I hope you have printed the slides which I have sent. Can you hear me? First? Yeah. Okay, good. So I have sent the slides, and probably it's nice if you print them, because I will sometime comment on what you see. And in the end of this bunch of the slides, you can find this one, right? I hope you see this. This is a spark chamber with a track of muon, track of the muon. That's another plot. Here are people involved in discovery of muon neutrino, and you see Bruno Pontecorvo, and here Steinberger, Leon Lederman, see? And Schwarz, Melvin Schwarz in the middle. So those guys got Nobel Prize for this discovery. I will start this lecture discussing implications of discovery of muon neutrino. Implications and consequences of new discovery. The experiment we have discussed, actually the experiment of searches for leptons of wrong type, or wrong type leptons. So this is kind of another name, if you want. Remember that muon neutrinos have been produced in pion decay because there is muon. And then what has been observed, that these muon neutrinos produce muons in the detector, but they do not produce electrons. And that led to conclusion that muon neutrino differs from electron neutrino, which would produce electrons. So you can formulate this scheme as searches for leptons of wrong type. So correct type, if you have muon neutrino and muon, electron is wrong type lepton here, right? Which doesn't correspond, it's not in the paper. So wrong type lepton. Remember this. The experiment we have discussed is considered as discovery of muon neutrino, because that satisfied criteria which we have already discussed before. That is, you produce neutrino in one space-time point and then detect its interaction in another space-time point and observe that this neutrino transfers momentum, energy, and quantum numbers. So from this point of view, this is completely satisfying this criteria of discovery of new neutrino. So it's discovery of with this discovery, and I have mentioned already, the doublet structure of weak interactions emerge. Now we can put electron neutrino and electron, muon neutrino and muon in kind of the same doublets, right? It's like a doublet. The meaning of this, that particles that enter doublet form charge currents, the corresponding charge currents. And remember, in our Hamiltonians, electron neutrino and electron form the charge current. And also muon neutrino and muon form the charge current. So doublet structure emerges. The third, in the experiments, in this one and in others, they always appear in this type of the pair. So either they are produced both electron and electron antineutrino, or electron neutrino produces electron, but they always appear in the pairs. That's actually the basis of introduction of new quantum number. So at this point, they actually introduced even two different quantum numbers. Let me write immediately Lepton numbers. You see, this is the origin or observational origin of introduction of Lepton numbers. So we see that something is conserved once you have always transitions of E and nu E, mu and nu mu. So we introduce Lepton numbers in the following way. So we introduce electron Lepton number, and this is introduced to match observational data. And muon Lepton number. And so for electron neutrino and electron, we introduce Lepton number 1, 1, and muon Lepton number 0 and 0. In contrast, for muon neutrino and muon, we introduce 0 Lepton numbers, but 1 muon Lepton number. Not only this, what we are saying, that these Lepton numbers are conserved, at least in interactions which we have seen so far. So Le and L mu are conserved Lepton numbers, quantum numbers. Which means that Le in the initial state equals Le in final state of your process. And I should add that these quantum numbers are additive quantum numbers. That is, if you have in a given state several leptons, then total lepton number of a given state is the sum of lepton numbers of the particles which enter this state. Also, I should add that the corresponding antineutrinos have opposite sign of these lepton numbers. So that, for instance, nu E bar antineutrino has -1, positron has -1, 0, 0, etc. So you can write this for muon antineutrino and mu plus. And you can check that the processes which we have discussed so far indeed conserve these lepton numbers. For instance, I have written pion decay as, say, pi plus, as mu plus, and muon neutrino. And clearly the lepton numbers are conserved. First of all, there is no electron lepton number here. So neither in initial state nor in final state. As far as L mu is concerned, in initial state it is 0, there is no leptons. Here in the final state we have -1 for mu plus and +1 for nu mu. And so in the final state we also have 0 quantum number. And all the processes which we have discussed, beta decay, muon decay, we always have this conservation of lepton number. By the way, for this reason, we are writing muon decay as, say, suppose it's nu minus, nu mu, then E minus, and electron antineutrino. And again, we have conservation of all two of both lepton numbers. For Le, we have 0 here, we have 0, 1, and this is -1. And L mu, is minus 1. This is 1. Nu mu is 1. And this is 0, and this is 0. And so we have conservation of both Lepton numbers. Another consequence. Another important consequence that soon after discovery of muon neutrino, lepton mixing has been introduced. In 1962, Maki, Nakagawa, and Sakata suggested that probably electron neutrino and muon neutrino do not have definite masses, but they are mixtures of other states with definite mass. So that electron neutrino is cosine theta nu 1 plus sine theta nu 2. And muon neutrino is orthogonal combination of these states nu 1 and nu 2. Therefore it's cosine theta nu 2 minus sine theta nu 1. So if nu 1 and nu 2 are orthogonal, then you can check immediately that also nu e and nu mu are orthogonal states. Nu 1 and nu 2 are states with definite masses. M1 and M2. And therefore, electron neutrino has no definite mass. It is a combination of states with different masses. So what is the meaning? Suppose you have electron neutrino beam, and you have mass spectrometer, which measure the masses. Of course, this is pedantic experiment. This is not what we are able to do. But then, in cosine square cases, square of this, you will observe the mass m1. And in sine square theta cases, you will observe the mass m2. So that the spectrum you will see will be like this. So that's m1. Let me put it in this way. So this is m1. Better like this. This is m1 and this is m2. Then this is the number of events. And then in cosine square theta cases, you will see m1. And in sine square theta cases, you will see m2. If you start with nu e. Now, if you have nu mu flux, then it will be opposite. In cosine square cases, you will see mass m2, and in sine square theta cases, the mass m1. So this is one of the consequences of this. And another one, actually, is the following. The point is that the phase of this component of electron neutrino and phase of this one is fixed. It's plus or 0. There is no phase difference. Here the phase difference is pi. So these states actually are coherent states. So nu1 and nu2 are in coherent state. We will discuss this later. So it's coherent states. Again, you see coherence appears. Coherent states. And the consequence of this is neutrino oscillations, which we will discuss at length later. Well, actually, Maki, Nakagawa, and Sakata already at that time suggested that it should be transmutation of neutrinos as a consequence of this mixing. So they said there is a transmutation of neutrinos, nu e and nu mu. That is, as the consequence of this description of nu e and nu e can be transformed into nu mu and back. So this is what we call oscillations. And in fact, oscillations have been introduced 6 years before by Bruno Pontecorvo again. However, Bruno Pontecorvo discussed oscillations of neutrinos into antineutrinos. Maki, Nakagawa, and Sakata discussed transformations of nu e and nu mu. This is what we call flavor oscillations. Questions?
I have a question. So the value of theta is a constant or is it a variable?
So this is what we call mixing angle. And if you are in vacuum, we are introducing this as a constant. Yeah, it's a constant. Remember before we introduced Habiba angle. And this is the same sort of parameter in the theory. Although we introduce Habiba angle as the mixing of currents, but eventually we will see that mixing of currents is reduced to mixing of quarks. And here we have mixing of leptons. Now, if you are in medium, well, it's a very important question actually. So first, the simplest way is just to assume that this is constant. However, it may be affected by medium. So if neutrinos are propagating in medium, then this angle can change. More questions?
I have a question. I mean, we are talking about Lepton Mixing, but we only do it for neutrinos. There is a way to mix like electron and mu?
This is actually the same story. So what is important is since nu e and nu mu enter the same doublets with electron and muon, this mixing has sense as a relative mixing. So you can introduce mixing for charged leptons, not for neutrinos. Okay? So we are saying that electron neutrino and muon neutrino are marked by the corresponding charged leptons. Okay? And then we introduce this mixing. But we can actually introduce mixing for charged leptons if you want. Physics will be the same.
Thank you.
More questions? Okay. So another consequence of discovery of muon neutrino is demand of quark-lepton symmetry. And we will discuss this later in details. Or if you want hadron lepton and symmetry. Because remember, in the case of hadrons or strongly interacting particles, we have the current which contains, say, proton and neutron. Although we then introduce some mixing. And it looks like you have a symmetry, right, between what happens in quarks, hadron sector, and the leptonic. In lepton sector, we have two doublets. Here we have just one with mixing. We can put here prime with mixing. And then it was idea that there should be some symmetry. And that was the reason to introduce eventually charm particles or charm quarks. We will discuss this later. So what is interesting, if you introduce such a mixing, it implies lepton number violation. Can one say why it is lepton number violation? Why this type of mixing should lead to lepton number violation? Of course, I already mentioned this transmutation. When your muon neutrino can be transformed to electron neutrino, this is lepton violating process. But how one can see already from this mixing that we deal with a lepton number violation? You see what I'm saying? And please do this. I can write this as an exercise. Nu1 and Nu2 have definite masses. What you can do, you can write the mass term. So the mass terms are M1, Nu1, Nu1, plus Nu2, Nu2, Nu2. So this is the meaning of the fact that we have definite masses for Nu1 and Nu2. Now, using this expression, you can invert them and represent Nu1 and Nu2 as a combination of Nu-E and Nu-mu. Please do this. This is a simple thing. And then you can insert this Nu1 and Nu2 in terms of Nu-E and Nu-mu into this formula. And what you will realize that for Nu-E and Nu-mu, you will have mass terms of the type this is E. You will have what we call off-diagonal or non-diagonal mass terms. Masses which actually connect electron neutrino and muon neutrino. And clearly this term in Lagrangian violates lepton number. So this term, lepton number violation. So please check this, that you have and express this mass M, E, mu in terms of Nu1 and Nu2. Finally, what I want to say, that all business of neutrino oscillations, which we are discussing now, emerges from this mixing scheme. And there are many studies which follow all this development. Studies of search for wrong sign, wrong type of lepton. So what is interesting, suppose you have the source of muon neutrino, like pion decay, like we have an accelerator. And what we have found is that it doesn't produce electrons. But what happens that the distance between the source and the detector increases, if you have a large enough distance, you start to observe electrons which are produced by originally created muon neutrino field. So, for large L, these wrong type leptons start to appear. So how come? And this happens because muon neutrino, just in vacuum, due to this mixing, can be transformed into electron neutrino. And those electron neutrinos produce electrons. So it's not like mu and e are not orthogonal. They are orthogonal if you put the closest, detector very close to the source. Their oscillations have no time to develop. So oscillation is some process which develops in time and in space. If the detector is very close to source, you do not see, so they have no time, no space to have this oscillation or conversion. For longer distances, as we established now, muon neutrino can be transferred to electron neutrino, and therefore this electron neutrino produces electrons. And you can see among the slides two detectors which actually observe this oscillation effects. One is T to K, and now it's more powerful even. And now we have, oops, not up here, and also NOVA experiment in the United States. You can see this slide. These are detectors which precisely detect this type of conversion. And for instance, NOVA experiment, it has distance. This is American experiment, and Fermi laboratory is the source, so the source of neutrinos is in Fermi laboratory, and then the detector is in Ash River, which is 810 kilometers far from the source. So one needs to have this almost like 800 kilometers for this process to develop. Questions? Well, actually, this is the reason why this experiment, to some extent simple, right, discovery of muon neutrino, got a Nobel Prize. You see how many consequences of fundamental importance emerge from this, the result of this experiment. You may have made much more sophisticated experiments which actually were not awarded by Nobel Prize. But this experiment did, because it has so many consequences and implications.
One question. This thing that you say that for large distances we can see a process that the muon, the neutrino goes to the electron neutrino, has to see also with this transmutation thing?
Well, this is the same. So I don't know why. They knew already oscillation term invented by Pontecorvo, and they referred to it, but they wanted to, to more probably underline that they more significant to see something. So they call this transmutations. But this term we didn't use it. We do not use this now. So that's. More questions? Now we start the second part of the course, which is leptons and quarks. And first of all, we will discuss how quarks were introduced and what is motivation for introduction of quarks. We have discovered just a few, discussed discoveries of few particles, but by 60s of last century, many more particles have been discovered already. Hadrons, or strongly interacting particles. And the notion of quarks emerged from classification of hadrons. Actually, the term of hadrons have been introduced by Lev Okun. And hadron means heavy. So hadrons like proton, neutron, so also lambda hyperons and many others are heavier than, for instance, lepton or muon. So hadrons. And hadrons now we are using for the particles which have strong interactions. So what are strong interactions? Let me remind. Strong interactions are responsible for nuclear structure. Those are short-range interactions. With radius, which is inverse of the mass of the pion, and as we saw, this is not accidental, and this is something like 10 to the minus 13 centimeters. And these are interactions which have high intensity. And the coupling constant, for instance, coupling constant of pion with proton or neutron, this coupling is much bigger than 1, at least at low energies. We need to ascribe this coupling to be bigger than 1. To reproduce cross-section, of course this is very naive estimation, but it's clear the coupling should be very big, because you want to reproduce cross-sections of scattering of proton on proton or pion on proton, and therefore you can match in the lowest order what should be the coupling in this case. The first step in classification is the introduction of mesons and baryons. And introduction of baryon quantum number. So, let me again write the hadrons. And I should add also the following, that motivation for this to for introduction of new number was certain features or properties of strong interaction. Put it here, of strong interaction. So it's not just we spontaneously introduce some new quantum number. We introduce it to explain certain properties of strong interactions. So, we have hadrons. Which are divided in two categories, mesons. And for mesons, like pi, like K meson, like rho meson. So pi and K we have discussed already. Those particles have baryon number 0. And again, prescription of quantum number is not just we are inventing something what we want. We are forced to introduce in this way. And then baryons. And those are particles like proton, neutron, lambda hadron, and many, many others. Also here there are many, many other particles. So for them we introduce B equals 1. And for corresponding antiparticles, the baryon number -1 for antiproton, antineutron, etc. We introduce the baryon number as additive quantum number again. Which means that if you have system of particles with different baryon numbers, the total baryon number of a given system is given by the sum of the baryon numbers of components of a given state. Now, another feature is that mesons have integer spin that is 0, 1, 2, etc. So pions and K mesons, as we discussed, they have spin 0. Rho meson has spin 1. In contrast, baryons have semi-integer spin. One half, 3/2, etc. Now my question is, why do we need to introduce another quantum number, since we can already distinguish baryons of these particles from mesons by just spin? So who knows why we still need to introduce another quantum number? Why spin is not enough? So why spin is not enough to make this classification and distinguish mesons from baryons?
Yeah, because we can add, we can have a process of 2 protons, for instance, and we can have spin 1 as the total spin. And that would correspond to mesons. Yeah.
So what?
Maybe we can have just the sum of the semi-integer spins that give us an integer spin and doesn't describe the same.
Some other ideas?
Maybe because I think the spin is not conserved. It's like we conserve the total angular momentum.
Yeah?
So we need something which is conserving one process to do experiment.
So
So we need a new quantum number to realize which process we can do with this kind of particle.
no, I'm not sure that I understand your argument. As I mentioned in the beginning, motivation to introduce baryon number. By the way, so if I ask during exam this question and you fail to answer, clearly you will be punished for this. So, so I have written that it's certain features of strong interactions which force us to introduce baryon number on the top of existence of different spins. And some of you were close. So suppose you have collision of two protons. If I just use conservation of spin or angular momentum without baryon number, then I would expect that processes like this, or when I have 3 pions in final state, should be possible, right? Because this system has integer spin. This system has integer spin, right? So, angular momentum conservation allows this process. However, it doesn't exist. And you see, here we have baryon number 2, and here baryon number 0. So this is the reason to introduce another quantum number. Like there are many other processes one can invent, for instance, pion interacting with proton doesn't produce in final state 3 protons plus some number of pions, because this baryon number of initial state is 1 and baryon number of final state is 3. And for this reason, because this baryon number is violated, this process doesn't exist. So not only we are introducing this baryon number, we state that B is conserved in strong interactions, but it also conserved in electromagnetic interactions and also weak interactions. Eventually we'll see this. So not only we are introducing baryon number, the important statement that we claim that this baryon number should be conserved. In this way, we can explain the absence of these processes. Okay? Next, very important notion and concept is isospin. And actually, whole kind of developments of the symmetry approach, applications of symmetry, can be already traced in this, on this example. And therefore, you really need to understand very well. Isospin. So what is experimental basis of introduction of isospin? The experimental basis is equality or approximate equality of mass of the proton and neutron. Well, later when pions were discovered, also it was observed that the mass of pi plus and pi minus close to the mass of pi 0, but that was later, as a spin has been introduced in 32, 33. So pions have been discovered in 40s. So this is one thing. And you see, if you observe some equalities of masses, then it always non-accidental. So there is something behind these equalities. So you always should ask questions of why they are equal, why they are close. So they are not completely equal. So the first question, why they are so close? Usually, some symmetries behind equalities. So equality implies certain symmetry. What is the second motivation? The second motivation is invariance of strong interactions with respect to interchange of proton and neutron. Or in other words, strong interactions of proton and neutron are the same. Are the same. That is, if you have the system, in a given system you substitute proton and neutron by neutron or vice versa. The strong interactions in this system will be the same. And the experimental fact which confirms this is similarity of energy levels of so-called mirror nuclei. So what are these mirror nuclei? These are precisely the systems when some protons are substituted by neutrons, and the classical example is tritium and helium-3. So here we have one proton and two neutrons. Here we have two protons and one neutron. So it's precisely the system when proton is substituted by neutron, and strong interactions are responsible for energy levels of this. So you can have a lower state, ground state of this nuclei, but you also can excite them like atoms. And then you will see some levels of this nuclei. And what happens is that these levels are very similar to for these two particles. So that strong interactions do not change when you substitute proton by neutron. Still, the energy levels are slightly different, because here we have two protons and they have electromagnetic interactions. So there are some repulsive forces. Here we have just one proton. And therefore, due to electromagnetic interactions of protons in helium-3, you have some addition to levels. So the levels are not exactly the same for these two nuclei, they are still different. But what is important, we can actually find out and compute what should be the difference due to strong interactions. In the first approximation, the energy levels are very similar. And actually this also tells you that, that strong interactions are stronger than electromagnetic interactions. So the electromagnetic interactions give kind of corrections on the top what you get from strong interaction physics. Again, equality of masses and equality of interactions of proton and neutron are the motivations to introduce isospin. The isospin had been introduced by Heisenberg. And actually the term of isospin has been proposed by Wigner. And what was the idea? The idea is that proton and neutron are just different states of the same particle. Which we call nucleon. In the same way as we have two polarization of electrons, proton and neutron are kind of states with different polarization of nuclei. So we use again analogy. And proton and neutron are analogy of electron with one polarization and electron with another polarization. And so that's the origin of the notion of isospin. Here we deal with spin, here we deal with isospin. So these are projections plus 1/2 and minus 1/2 on the, for instance, the third axis in the space. In the same way, proton and neutron are different projections of the same particle in the isospin space. So this is already the first when we have appearance of internal space. So that's external space. Here we deal with internal space, polarizations in internal space, and then transformations in internal space. So here we can introduce isospin and the third projection of isospin, and then the proton has a third projection of isospin 1/2 and neutron minus 1/2. Now, electrons with two different polarizations have the same electromagnetic interactions. The idea is that proton and neutron, being just different projections on the isospin third axis, have the same interactions, but now strong interactions. Okay? Now, electromagnetic interactions are invariant with respect to interchange of two polarizations. And now, again, by analogy, we are saying that proton and neutron, so strong interactions, are invariant with respect to these rotations or permutations and change of a third projection of isospin. Now, let me show how we parameterize this. Again, physics basis is that we have the same interactions, strong interactions of proton and neutron. Now you will see. Let me find. Oops. Let's see if that will be enough. So, how do we parameterize this? Formalized. Formalize this. So we are talking about proton and neutron, and they have the same strong interactions. this means that strong interactions are invariant with respect to permutations. And more precisely, what is invariant? Hamiltonian of strong interactions is invariant with respect to permutation. So, the fact that we have the same interactions of proton and neutron is formalized by the fact that the Hamiltonian or Lagrangian of strong interactions is invariant with respect to permutations of proton and neutron. Total Hamiltonian can be written as the Hamiltonian of interactions plus Hamiltonian part of mass terms. Well, actually the fact that the proton and neutron have the same masses refers to this, and the mass terms here should have the same masses for proton and neutron. And now we are focusing on this interaction part. In general, the Hamiltonian should be expressed in terms of operators or the fields of proton and neutron, right? Like electromagnetic Hamiltonian of electromagnetic interaction, it is the function of the fields of electrons and photons. So what is important again? Remember this. We may not know explicit form of this Hamiltonian. In fact, it's very complicated. So you can write something. Well, actually, we have some exercise to write something, but it doesn't mean that in the case of strong interaction it describes correctly things. But what is interesting, if you have symmetries or assume symmetries of your Hamiltonian, then you can extract many physical consequences, even not knowing precise form of Hamiltonian. Symmetry is extremely powerful tool, actually. So, let me move a little bit further. And I think I need to come and to take some piece of show. Oh, no, there's not. So it's kind of going to the end. So let me now describe what the meaning of invariance of the Hamiltonian. With respect to permutations. We can introduce transformation, which corresponds to permutation. And I introduce this permutation as 0, 1, minus 1, 0. Of course, I can take this also plus 1, but for the further, for me it will be important to have minus 1 and determinant equal to 1, because in this case I can embed this into SU2, which is actually a wider symmetry. So at this point we just discussed one transformation. Remember, rotation in usual space when we do the electron with two different polarizations, it's continuous transformations in three-dimensional space. The same is here, so the symmetry, which we will eventually have, the isospin symmetry, is not just this permutation, it's more wider symmetry. And I will focus on this a bit later. So we introduce this transformation and introduce Coulomb, proton and neutron. And then permutation can be described as action of this transformation onto P and N, which gives me N and P. So it's not only permutation but appearance of minus sign, but it doesn't matter. So we are changing proton to neutron. We can call this N nucleon, and so our transformation are U acting on this nucleon doublet, which gives to us N prime. And N prime is this one. But I want to keep the general consideration. So we have this we introduce this transformation. Now the third thing, if you want to construct Hamiltonian, which is invariant, under this transformation, we should be able to write the Hamiltonian as a function of N, and not separately proton and neutron, but proton and neutron should enter the Hamiltonian as this whole object, doublet. So this is one of the conditions to have invariance. So now I want to discuss invariance of the Hamiltonian. Okay? Good. So, let me take this equality, and I can express N as U minus 1 inverse transformation N prime. Okay? From this. And then I can insert this N into Hamiltonian. And what I get is U minus 1 N prime. Right? And now invariance means that I can reduce this Hamiltonian to the form H N prime. So this is the meaning of invariance. The form of the Hamiltonian is the same in terms of N, our original field, and in terms of transformed field. So what doesn't change, what is invariant is the form, shape of our Hamiltonian. We are doing transformation. We introduce new prime, so N prime, insert in the Hamiltonian, and if we can reduce this to the same form but in terms of new variable, then we are saying that the Hamiltonian of Lagrangian is invariant. Of course we can introduce some other transformations, and that will not be the true, so it's not always we can reduce this expression to this one. But if we can, then we will get, then we can claim that there is invariance. This type of the exercise, please try to think about, and actually in the last part of the course when I will discuss in details the symmetries, I will give you a very simple example when we do rotations of coordinates, x and y, and then we do in 2 dimensions rotations, x prime and y prime. And remember, so if I have circle, right, which is x squared plus y squared equals to something, right, equals a squared. Now, if I do rotations in x and y, and so I introduce new variables, x prime and y prime, and under rotations, when I insert in my circle equation, I will get the same equation, but x prime squared plus y prime squared. And therefore the circle is invariant, or it is symmetric, it is invariant with respect to rotations. Okay, this is a simple example. Think about this, and this is complete analogy to what I'm saying here. Now, as I said, this is one of the examples, one of the transformations. But actually the isospin group And especially if you are using analogy with what we have in the case of electron, is wider, is bigger. It's not just one discrete transformation. So actually, this transformation with 1 minus 1, 0, 0 is part of the transformations of SU2 group. So you had this course, right? So you know what this SU2 group is, this group which in 2 dimensions of rotation given by matrices 2 by 2, the fundamental, right? Complex matrices, and this is special group, the determinant is 1. And this is unitary group. So this transformation belongs to this, and we can claim and check eventually that in fact proton and neutron are transformed with respect to SU2. So they form doublet of SU2, which transform under fundamental representation of SU2 group. So this doublet is transformed. We are saying sometimes representation 2, or this is fundamental for SU2, transformed by fundamental representation. Of SU2. So, this is only the first step. So we are introducing bigger transformation, group of the transformation, not just permutation, but SU2 group of transformations. And then we claim, again, that Hamiltonian of strong interactions is invariant with respect to SU2 transformations. In the same way as we did here, so we just use U, but you can take any matrix 2 by 2 from SU2 group. And we kind of, first of all, hypothesize, right, that probably strong interactions are invariant with respect to SU2 transformations. And proton and neutron are transformed, form the doublet of this group, and transform under the SU2 transformations. And then we claim that strong interactions are invariant with respect to these transformations, precisely in this sense. Well, you see, here, this transformation is simple. It's just switch proton and neutron. General SU2 transformation will produce for you some combination. So what you will have here, not just N and proton, but you will have here some combination of N and P, and here combination of N and P with some coefficients, A, B, A prime, B prime, okay? That will mix all the components. And still you will get invariance. So to say, when you do this, you will get the Hamiltonian, which is invariant with respect to these transformations. Once we introduced this SU2 group as a symmetry group of strong interactions, the important point is that the group itself allows us to make classification of particles. SU2 group has 3 generators, as you remember. One of them sigma 3 is diagonal. So it's 1 minus 1, and we can introduce I3 as sigma over 2, and it will be 1/2, 0, 0, minus 1/2. And if we act by this I3 onto proton, by the way, proton now can be described as 1 and 0, and neutron as 0 and 1. And therefore, acting by I3 on proton give us 1/2 on proton, right? Because of this. And proton has non-zero component up. And I3 acting on neutron gives minus 1/2 neutron, and therefore we can consider proton and neutron as eigenstates of operator I3 with eigenvalues 1/2 here and minus 1/2 here. So, and these are actually parameters which enter this generator. It's 1/2 and minus 1/2. And the general rule, if you have some symmetry, if you have diagonal generators, then the elements of these diagonal generators correspond to quantum numbers, which you can ascribe to the particles. Questions? Well, I need to take a piece of chalk, so I will go to some other office, and please think if you have questions. Try to digest this. Questions? So we assumed that Hamiltonian of strong interactions, let me repeat, is invariant with respect to SU2 transformations. This invariance ensures that the strong interactions are the same for proton and neutron. It actually gives much more consequences, because it's enough to use just a permutation transformation to describe equality of interactions. The symmetry with respect to SU2, which is of course much bigger than just permutation, leads to many consequences. It leads eventually to relations between different amplitudes of scattering of probabilities. Okay? So we have discussed so far proton and neutron. Later, the system of pi plus, pi 0, and pi minus. So these particles have been discovered. And the masses of these pi 0, pi plus, and pi minus are approximately the same. The story is similar. And the interactions, strong interactions of these pions are the same. And therefore, we can claim that these particles form triplet. Now it's triplet of SU2. Or they are transforming under a joint representation of SU2. And the meaning again is the same. So they transform, and under these transformations, Hamiltonian of strong interaction doesn't change. And in this representation, I3 is given by 1, 0, minus 1. So that's here the operator of third projection of isospin. Okay? So now let me discuss the issue of isospin and electric charge. So we have proton and neutron, which have third projection of isospin 1/2 and minus 1/2, right? And they have electric charge, which is 1 and 0. So there is a change of third projection by 1 unit here, and change of the charge, electric charge by 1 unit here. And it seems that isospin and electric charge should be related somehow. So that Q, electric charge, should be proportional to, or should contain I3. But it should be something else here to reproduce electric charges. And what is staying here is baryon number over 2. And then you can check that this formula reproduces correctly electric charges. Actually, this kind of empirical formula has very deep physical meaning, which you'll realize later. For the time being, we're just tuning parameters or characteristics of our particles to have this relation. Okay? So now let's go to strange particles and to see what's going on if you want to include strange particles into this scheme. So we have the system of K-mesons. Let's take K-mesons. And what has been discovered? 2 doublets of K-mesons. K minus. Remember, these particles have strangeness. And therefore, in contrast to pi 0, K0 and K0 bar are different particles because they have opposite strangeness. So this has strangeness plus 1, and therefore antiparticles should have strangeness minus 1, and therefore they are not coinciding here, it's different particles, and it was established that actually we have K plus, K minus, K0 and K0 bar, and we can arrange these particles in two doublets which have certain strangeness. So this strangeness is 1, and here the strangeness is minus 1. Now, binary number is 0 for K mesons. And now we can write the formula for electric charge. Again, the change of the charge is by 1 unit, and therefore it should be I3 plus what? So what you would add here to have correct charges? So let us generalize this formula. Formally write B, although B is 0 and doesn't change anything here, but it has strangeness. And we can write here add strangeness. And writing in this way, with this assignment of strangeness, we can reproduce electric charges of this system. Okay? So this is the formula which have been derived by Nishijima, Nakano, and then Gell-Mann, and usually it refers to Gell-Mann-Nishijima formula. I don't know why Nakano appears, by the way, Gell-Mann. Gell-Mann-Nishijima formula. Again, we introduce it kind of empirically, so clearly it should be some relation, but again it has a very deep meaning when we start to work on operators and operators of physical quantities and embedding everything in wider groups. So that has been done in 1953. I think Gell-Mann paper was later. That expression allows to us, and we will see actually that already in SU3, this is the group which we are coming to, this writing has very deep meaning. We can introduce hypercharge as B plus S. And then our formula for electric charge becomes I3 plus Y over 2. In SU3, this corresponds actually to SU2 subgroup, and this is to U1. Just to give a hint that eventually that has a really deep meaning also in the group theory context. So we start to discuss and continue on Monday. The next step, so far we have introduced isospin, right? So we introduced isospin and claim that there's invariance of strong interactions with respect to isospin transformations. That has been actually confirmed in many ways, so that kind of first was the idea. And then it was confirmed by many observations, because again, isospin symmetry has much more consequences that we started with, the equality of masses and this equality of similarity of nuclear levels. So it goes much beyond, and predicts the existence of relation between cross-sections of different processes, of scattering, for instance, pines on nucleons, or nucleons on nucleons, or pines on pines. And the symmetry allows to actually reduce many different amplitudes and cross-sections to just a few. And then using the symmetry, you can get the expressions for cross-sections for other processes. So this is the power of the symmetry. Now let me start this topic and then we will continue later. Families of hadrons. As I said, many particles have been observed by that time. And what you are doing first zoo, so try to classify first, or to put them in some clever way to understand eventually which kind of the physics is behind. And so what has been done, the families of hadrons have been identified, and there are certain differences and similarities which allow to combine, what is the principle, to combine some particles in the same family. So what are common for, let me write here, families of hadrons, and what is common for all components, common for all components of family, of a given family, is baryon number, spin. So let me put, I don't know, because strangeness is spins here, spin and parity. So all members of a given family have the same baryon number, spin, and parity. What distinguishes, which characteristics distinguish components of a given family? Electric charge. So in a given family we will have the particles with different electric charges. Different strangeness or hypercharge. I don't know, so this is strangeness. Let me put here. Strangeness. In contrast to the spin here, which is common strangeness. Or alternatively, you can describe different components of a given family by the third projection of either spin and strangeness. This is more close to kind of group theoretical analogy or mapping of what's going on. But these are the same characteristics if you take Gell-Mann-Nishijima formula. You can use this or that one. So this is common for a given family, and these are differences. So we will have family with a certain baryon number, strangeness, and parity, and the different elements or different components of the families differ by the third projection of either spin and strangeness. Questions? So, again, let me remind you, if you want to have some more discussions, and we can meet in person, so you can send me mail if you want to discuss, and make some appointment, and we can discuss in some details. And please, think about this. Think about the symmetry and invariance, because starting from this discussion, that will appear always. So starting from this, we will use these terms of the symmetry and in invariance. That's our terms, our kind of language in particle physics. And that you should understand very well. Again, coming back to example with just a circle and rotation. Clearly, that circle is invariant under rotation. Thus it changes, right, when you do rotation. Formalize this, so you introduce, which is analogy of what we did, so you can introduce initial coordinate x and y, then do transformations which correspond to rotation. You will have x prime and y prime, and then you insert in your equation of circle, and you will find that the expression in terms of new coordinate x prime and y prime will be the same. Please repeat this. Convince yourself that you understand this. And what we are doing is analogy. Okay?
I have like two questions. The first one is like we have the German-Nishima quantity group with the charge and HEP-PP. Could we show it like empirical? There is a way to derive it from the Hamiltonian, or it's just empirical?
No, we are not using Hamiltonian to write these formulas. We just have assignment of electric charges and strangeness, and then we just saw that there are some relations between them. So, more deep understanding comes when we do this group theory stuff. So we introduce operators, and we will see that actually, I have written it somewhere, that we have SU3 eventually, the group which is the group of strong interactions. So that's what we are we'll discuss next lecture. So SU3 can be broken to SU2 cross U1.
Yeah.
And therefore, so this guy has one diagonal element, remember, so it's sigma 3. This one is also diagonal. And then you can derive from this expression using SU3. So we are moving to reconstruct this SU3. So next step will be to have these features. We will come eventually to SU3.
Okay.
So for time being, it is just observation, if you want.
So,
One point is, of course, so you have clearly change, so you have these multiplets of different hadrons. Change of the charge inside the component, inside these doublets, is by 1 unit. And the same what I3 is doing, right? So this already gives some hint that probably there are some connections between electric charge and a third projection of isospin. And then we see that it's not just straightforward connection. You need to add something to have this for all the particles. By the way, for pi 0, pi plus, and pi minus, it's just I3, no need to add anything. So for triplet, pi plus, pi 0, pi minus, electric charge is just I3. Also because baryon number is 0 and also strangeness is 0 for these particles. And for a joint representation, I3 is precisely 1, 0, minus 1. Okay? Now this is the simplest relation. Looking at this, you say, okay, yeah, sure, electric charge is the same as isospin, set projection.
Okay, see. I have another question. We saw the lepton number was conserved, but then we saw that for long distance, we can relate the lepton number conservation. So my question is, do we have another quantum number which we can relate in some like distance, long distance or another thing? Or not?
Well, no, we do not introduce any additional quantum number related to the distance. So what we have in this case, we are saying about, first of all, lepton number conservation. Lepton number is conserved by usual weak interactions, usual which are proportional to Fermi coupling constant. This kind of Lagrangian, which we have discussed for pi decay, for beta decay, for muon decay, all these Hamiltonians are invariant with respect to lepton number. What violates lepton number are mass terms, not interaction terms, but mass terms. And I told you, please convince yourself that mixing implies already non-conservation of lepton number. So that the interactions which are responsible for masses break lepton number. And as we discussed already, we have different type of the interactions. Different type of the interactions have different symmetries. They respect or not respect different quantum numbers. So of course there are some, it looks like some quantum numbers which are conserved everywhere. It looks like this electric charge is conserved everywhere. At least what we know. But some other quantum numbers, they may be conserved in just some interactions, but are broken by other interactions, like isospin. Isospin is very good symmetry of strong interactions, but it is not respected by weak interactions.
Thank you.
And now, so this distance, yeah. So you see, we have just standard weak interactions which produce neutrinos, right? So, and lepton number is conserved. The processes which are related to this lepton number violation, they develop in the course of propagation. So this is what happens. But they are due to some still interactions which violate lepton number. These are eventually interactions with Higgs field, if you want, which we haven't discussed, of course.
Thank you. Thank you.
Okay? Then see you on Monday. We will continue with families of hadrons. And prepare your questions, and again, if you have, if you want to discuss in some more details, send me mail and we will arrange some meeting. Okay?